Welcome students to the MOOCs series of lectures on advanced probability theory. This is lecture number 29. As I said at the end of the last class that today we shall be studying central limit theorem, a very important concept of probability which in short we call CLT. Over the last few lectures, we have been studying convergence of a sequence of random variables. So, first we studied mode of convergence, here we looked at convergence in distribution, and also we have looked at convergence in probability and almost sure convergence. If we look at their applications, we have seen laws of large numbers in particular, say weak law of large numbers. Here we have checked that the average of a sequence of random variables converge in probability to the average of their means. If we look at it from convergence towards the random variable, then we find that the average of the sequence of random variables converge in probability to a degenerate random variable. That is a random variable that takes only one value, namely the average of the means with probability 1. Here we do not talk about how the sequence of random variables behave with respect to all x belonging to R. As our focus is on average of the means of the random variables. Hence, convergence in probability makes sense. But we may be interested in the asymptotic behavior of this sequence of random variables that is, if x1, x2, xn is a sequence of random variables, what is the asymptotic behavior of Sn is equal to sigma xi I is equal to 1 to n as n goes to infinity. Now, some of you may not know the meaning of the word asymptotic. So, here I define for you. Asymptotic means becoming increasingly close, increasingly exact as an underlying variable approaches a limit, that is, if we consider x1, x2, xn, what will be the asymptotic behavior of Sn as a random variable, or in other words, we look at whether Sn asymptotically approaches some known distribution, say f x, that is, does there exist any distribution function f x such that probability Sn less than equal to x converges to f x as n goes to infinity. In central limit theorem, we study this behavior of a sequence of random variable x n as n goes to infinity. Now, the best representative of a distribution is its moment generating function or MGF. From uniqueness theorem, we know that for each random variable x, m x t, that is moment generating function of x at t, is unique if it exists. Hence, to study asymptotic behavior, as a random variable of x n, a sequence of random variables, we look at m n t, that is the MGF of x n, and tries to see if m n t converges to m x t for some random variable x. Hence, our focus is on limit n going to infinity m in t. However, the problem is that even though m n t's are valid moment generating functions, limit n going to infinity m n t is equal to m t need not be an MGF. That is, the sequence of moment generating functions converging to something which is not a moment generating function itself. Example, let x n be distributed as follows. It takes the value n with probability one. That is, x n is a degenerate random variable which takes the value n. Then what is m n t? M n t is equal to expected value of e to the power t x is equal to e to the power t n if t not equal to 0 and is equal to 1 if t is equal to 0. Therefore, we are looking at m t is equal to limit n going to infinity e to the power t n. Now, if t is greater than 0, e to the power t n goes to infinity, that is, does not converge, and if t is less than 0, e to the power t n goes to 0. Therefore, m t is equal to 0 if t less than 0, 1 if t is equal to 0 and infinity if t is greater than 0. Therefore, m t cannot be an MGF, since to be an MGF we need t greater than 0 such that it converges for minus t to plus t. Hence, we look at situations when limit n going to infinity m n t exists. Example, let x n be a sequence of binomial random variables that is, x n is distributed as binomial n comma p such that the expectation n p remains constant. Does x n converge to some random variable? That is the question. So, let lambda be the constant expectation. Therefore, n p is equal to lambda. Therefore, p is equal to lambda by n. Therefore, q is equal to 1 minus lambda by n. We know that the MGF of binomial n p is equal to q plus p e to the power t whole to the power n. Therefore, in the above scenario, m n t is equal to 1 minus lambda by n, that is q, plus lambda by n e to the power t whole to the power n is equal to 1 minus lambda by n into 1 minus e to the power t whole to the power n. We know that limit n going to infinity 1 minus x by n whole to the power n converges to e to the power minus x. Therefore, this MNT converges to limit n going to infinity e to the power minus lambda into 1 minus e to the power t. This is the MGF of Poisson random variable with parameter is equal to lambda. Therefore, in the above case, with the restriction on NP is equal to lambda, we see the sequence of random variables xn converges to Poisson with lambda. Let us now consider another example. Suppose x1, x2, xn is a sequence of random variables such that xn is distributed as Poisson with parameter n. Question is, does xn converge to some known distribution? Answer: let us consider yn to be a sequence of random variables such that yn is equal to xn minus n over root n. We know that if x is distributed as Poisson with lambda, then expectation of x is equal to variance of x is equal to lambda. Therefore, x minus lambda upon root over lambda is the normalized form of x. Because it is variable minus mean divided by standard deviation. Therefore, yn, which is equal to xn minus n over root over n, is standardized or normalized xn. What is the MGF of yn. We know that if x has the moment generating function mxt, then for constants a and b, the MGF of ax plus b at t is equal to e to the power bt into MGF of x at the point at. Therefore, MGF of yn is equal to moment generating function of xn minus n upon root n at t. Note that b is equal to minus root n and a is equal to 1 upon root n. Therefore, MGF of yn is equal to e to the power minus t root n into MGF of xn at t upon root n. Now, MGF of Poisson random variable with parameter lambda is equal to e to the power minus lambda into 1 minus e to the power t at t. Therefore, MGF of xn at t over root n is equal to e to the power minus n into 1 minus e to the power t by root n. Since here lambda is equal to n, n is equal to exponentiation of, I am writing this as exponential function, minus n into 1 minus e to the power t by root n is equal to exponentiation of minus n into 1 minus. Now, let us expand e to the power t upon root n. This is equal to 1 plus t upon root n plus t square upon 2 n plus t cube upon factorial 3 n to the power 3 by 2 plus terms having n square or higher power of n in the denominator. Is equal to exponentiation of minus n into this one cancels with this, therefore, minus t by root n minus t square upon 2 n minus t cube upon 6 n to the power 3 by 2 minus terms with higher power of n in the denominator is equal to exponentiation of t root n plus t square upon 2 plus t cube upon 6 square root of n plus terms with n or its higher power in the denominator. Therefore, MGF of yn is equal to e to the power minus root n into t multiplied by exponentiation of this term, that is t root n plus t square upon 2 plus t cube upon 6 into n to the power half plus terms with higher power of n in the denominator is equal to e to the power minus root n t plus root n t plus t square by 2 plus t cube upon 6 n to the power half plus other terms is equal to e to the power t square by 2 plus t cube into 6, this is 6 equal to factorial 3, n to the power half plus other terms. Therefore, limit n going to infinity m y n at t is equal to e to the power t square by 2, because all these terms are going to 0 as n goes to infinity. Therefore, the MGF of y n t converges to e to the power t square by 2, which is the MGF of standard normal with parameters 0, 1. Therefore, if x n is a sequence of random variables such that x n is distributed as Poisson with parameter n, then as n goes to infinity, x n converges in distribution to normal 0, 1. Note that Poisson is a positive random variable, whereas normal 0, 1 takes values in minus infinity to plus infinity. Hence, we need to standardize or normalize x n with x n minus n upon root over n. So, what happens is the following. X takes values 0, 1, 2, etc. Therefore, x minus n upon root n takes values from minus n upon root n when x is equal to 0 to infinity. Therefore, as n goes to infinity, x n minus n upon root n takes values from minus infinity to infinity. Hence, the above approximation makes sense. Another example, let x n is distributed as binomial with n p. What is the limiting distribution of y n is equal to x n minus n p upon root over n p q. Therefore, here too we normalize it such that mean of y n is equal to 0 and variance of y n is equal to 1. Therefore, we need to obtain limit n going to infinity m y n at a point t is equal to limit n going to infinity m x n minus n p upon root over n p q at the point t is equal to e to the power minus n p t upon root over n p q into m x n upon root over n p q at the point t is equal to e to the power minus n p t upon root over n p q into m x n at t upon root over n p q. We know that the moment generating function for a binomial random variable is equal to q plus p e to the power t whole to the power n. Therefore, mgf of y n is equal to e to the power minus n p t root over n p q multiplied by q plus p e to the power t upon root over n p q whole to the power n is equal to e to the power minus p t root over n p q multiplied by q plus p e to the power t upon root over n p q whole to the power n is equal to q e to the power minus p t root over n p q plus p times e to the power minus p t root over n p q plus t root over n p q whole to the power n is equal to q times e to the power minus p t upon root over n p q plus p times e to the power t into 1 minus p upon root over n p q whole to the power n is equal to q times e to the power minus p t root over n p q plus p times e to the power q t root over n p q whole to the power n. Therefore, question is, what is the limit of q times e to the power minus p t root over n p q plus p times e to the power q t root over n p q whole to the power n. So, we do this by expanding these exponential terms. Therefore, we are writing it as q times 1 minus p t upon root over n p q plus p square t square upon 2 into n p q minus p cube t cube upon n to the power 3 by 2 p q to the power 3 by 2 into factorial 3 plus terms with n square or higher power in denominator plus p times, now we are expanding this 1 plus q t upon root over n p q plus q square t square upon factorial 2 into n p q plus q cube t cube upon factorial 3 n to the power 3 by 2 p q to the power 3 by 2 plus, like as before, higher powers of n square in the denominator whole to the power n is equal to, now we are adding. So, we get q plus p minus q p t plus q p t, therefore, they get cancelled, plus q p square t square plus p q square t square upon 2 n p q plus terms with n to the power 3 by 2 or higher powers of n in the denominator is equal to 1 plus, if we take p q common, it is t square upon 2 and that p q cancels with this plus n plus other terms whole to the power n. Therefore, moment generating function of y n is equal to, what we get from here is 1 plus t square upon 2 n plus terms with n to the power 3 by 2 or higher powers of n in the denominator whole to the power n. Therefore, log m y n at t, here also there should have been a t, is equal to n times log of 1 plus t square upon 2n plus such terms is equal to n times t square upon 2 by n plus terms with higher powers of n in denominator is equal to t square 2 plus terms with power of n in the denominator. Therefore, limit n going to infinity log of m y n at t is equal to t square upon 2, as other terms go to 0, implies limit n going to infinity m y n to the power of t is equal to e to the power t square by 2, which is the MGF of standard normal 0 1. Therefore, here too we find that the MGF converges to MGF of Z, which is equal to normal 0 1. Question is it a fluke? The answer is no. In fact, this is what central limit theorem suggests. So, what is central limit theorem? In its most general form, it says if x n is equal to 1, 2, etc., is a sequence of independent random variables with mean mu I and variance sigma square I for x I, then S n is equal to x 1 plus x 2 up to x n is asymptotically normal with mean is equal to sigma mu y and variance is equal to summation sigma I square, I is equal to 1 to n, here also I is equal to 1 to n. So, this is the most general form when the only assumption is that x 1, x 2, x n are independent. In this class, we shall not prove this. What we shall prove, that if they are not only independent, but identically distributed, then same result holds. Okay, students, I stop here today. In the next class, I shall start with this statement. Thank you.